Chapter 4 deals with alkanes and cycloalkanes. Alkanes are hydrocarbons, and hydrocarbons are compounds that are only composed of hydrogen and carbon. So you can see a couple of examples here that have varying degrees of saturation. So this is the fully saturated ethane. We add a double bond that makes it ethylene, triple bond makes it acetylene, and then benzene here has 4 rings or double bonds. Saturated hydrocarbons do not contain any pi bonds. You can see all of these have single bonds only. So those are saturated hydrocarbons. So back in the olden days, compounds were named by whomever discovered them, so they could name them whatever they wanted. So formic acid came from ants because it was isolated from ants and named after the Latin word for ant, which was formica. Urea was isolated from urine, so they called it urea. Morphine was a painkiller named after the Greek god of dreams Morpheus, and in 1892 the chemists decided that a systematic naming system was needed so that we weren't naming things willy-nilly. And so now we can use this IUPAC system instead of having to memorize a common name for every single molecule. So the IUPAC system comes from the International Union of Pure and Applied Chemistry. So the first rule in naming alkanes is to find the parent chain, which is the longest consecutive chain of carbons. So in this example, if you just look from left to right, this is a 1, 2, 3, 4, 5, 6 carbon chain. But after you look for a while when you're counting the longest carbon chain, the longest one actually has 9 carbons. So the longest carbon chain is shown there. So that's the longest carbon chain out of there. And there are branches that come off of that. After you find the parent chain, you want to match it up with its parent name or the prefix. So for 9 carbons, it would be non, and with a 9 carbon chain with no branches would be nonane. We have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. So you will be responsible for knowing 1 through 10. There's not very many occasions in which you come across pentacone, which is 50 carbons, or hectane, which is 100 carbons. If you can remember prefixes for 1 through 10, you should be okay for this class. After you find the parent chain, if there is more than one correct possible carbon chain, you want to choose the one with the most substituents attached. So a substituent is a branch that's coming off of here. So both of these have 7 carbon atoms as their parent chain, making them heptane. The one on the left here has 3 substituents, and this one has 2 substituents. And although it seems counterintuitive, you actually want to choose the one that has more substituents. If the parent chain is cyclic or a ring of carbons, you just add the name cyclo to the beginning of the parent name. So this becomes cyclopropane, cyclobutane. This is cyclopentane. In this case, the parent has the longest carbon chain here is 8 carbons. This is cyclooctane. The parent name may not include carbons that are both in and outside of the ring. So the parent here is cyclooctane. It would not be nonane. If you have a cyclic structure that's coming off of a ring, this has 3 carbons. This has 5 carbons, so the parent is going to be pentane here, not cyclopropane. And that's because we're looking for the longest standalone carbon chain. This has 5 carbons versus the 3 carbons. So after you have the parent chain, you want to identify the substituents. And if you recall, we want to use the parent that includes the most number of substituents if it's tied. So then count the number of carbons in each side group and use the terms from table 4.2 to name the substituents. And those will have the same prefix, but we'll just end them in -yle instead of -ane. So this parent, 10, this would be decane. The substituents, this has 1, 2 carbons, so this becomes an ethyl. 1, 2, 3 becomes propyl, and 1 is methyl. So some substituents have complex branches. So this is the parent chain here. And this group has 5 carbons, but this is not a pentyl group. And we can't name it as a pentyl group. So some of these branch substituents have common names that you may want to memorize because we will use them more frequently than their IUPAC names. So a branched carbon with 3 atoms, if it has the 1, 2, 3, and it's a straight branch coming off of there, this is a propyl group. And when you have the group that looks like a Y here, this is an isopropyl. The name in parentheses is the IUPAC name, so it's one methyl group coming off of an ethyl on the first carbon there. So that's how they name that, but isopropyl is the one that we use most commonly. For substituents, again with complex branches, when you have 4 carbon atoms, this is a butyl group. So that's a straight butyl group. If the parent is coming off of the second carbon, this is a sec-butyl. And then if you have this iso group here, like you did in the last one, that Y shape, this is an isobutyl. And then this one is tert-butyl for tertiary butyl group. This one looks like a turkey claw. And the 5 carbon chain here, this is a pentyl group. If it has that Y at the end, this is isopentyl. And this one is neopentyl. So we'll come across a lot of these. You won't have to worry about naming neopentyl groups. We don't see those very often, but that looks like it's a tert-butyl group with the CH2 here. So when you're naming the compounds, you want to number in sequence the consecutive carbons in the parent chain. The number or locant is used to communicate where each substituent is attached to the parent chain. So these are both pentane. So you can think of pentane as the street name. The number where the group is the address. So we have a 2-methyl. And that's because this is a group that's coming off of there. It has 1 carbon. This is a 1 carbon. This is 3-methyl. These molecules are isomers because they have the same parent name, but their full name is different because they're not identical. So they're constitutional isomers of each other. Different name, same formula, different structure. When you're numbering, if one substituent is present, you want to number the chain so that it has the lowest number possible. These are both the same structure. One is numbered left to right, the other is right to left. This one gives the substituent at 2, while this one is at 6. So this is the correct one. So you want the lowest overall numbering. If you have multiple groups, you want to number the parent chain to give the first substituent the lowest number possible. This one is 2, 5, 5. This one is 3, 3, 6. This one is the correct one. So the first substituent should have the lowest number possible. If there's a tie, number the parent chain so the second locant gets the lowest number possible. This would be 2, 3, 6 versus 2, 5, 6. So this is the correct one. So the second number should get the lowest number possible. If there's no other tiebreaker, then assign the lowest number alphabetically. So you can number this as bromine 1 through 5, put the chlorine here, or it would be chloro first. This is the correct way. And that one is the incorrect way. So 1 bromo is better than 1 chloro. And in the cyclic structure, you will also do the same thing with numbering. This one is 1, 1, 3. This would be 1, 3, 3. So this one is incorrect. So to put the name together, you would assign a locant to each substituent and list them before the parent chain in alphabetical order. If you have multiple groups like we saw previously with the 3 methyl groups, you would use a tri prefix, or you can use di or tetra if you needed. Tetra is for 4, penta is for 5. That's if the multiple substituents are the same. And then prefixes are not used for alphabetical purposes except for the prefix iso. So if you had 2 methyl groups, it would be dimethyl, but you would alphabetize by M. But if you had an isopropyl, it would be di-isopropyl. So this is the correct way. So when you're numbering the carbon chain, you want to number the parent chain to give the first substituent the lowest number possible. This one is 1, 1, 3. This one is 2, 5, 5. This one is 3, 3, 6. So this one is the correct one. If there's no other tiebreaker, then assign the lowest number alphabetically. So you can number this as bromine 1 through 5. This one is 2, 5, 5. This one is 3, 3, 6. So this one is the correct one. you would alphabetize by I, and that's only for the isopropyl. This one here, you have 1, 1, 3, trimethyl, and you have to list where each of those groups here. So the trimethyl tells me I have 3 methyl groups. 1, 1, 3 tells me I have a methyl group at 1, 1, and 3. This is cyclohexane. This we would number this way. This would be 1, 2, 3, 4. This is an isopropyl group, and these are methyl. Just to summarize, you're going to identify the parent chain, so that's the longest consecutive chain of carbons, identify the name and substituents, number the parent chain and give the substituent a prefix if needed, and you want to give that first substituent the lowest number possible. List the numbered substituents before the parent name in alphabetical order, and ignore prefixes like di, tri, tetra, except iso when ordering alphabetically. So to name this one, we got to find the longest carbon chain. So if I number this way, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So the longest chain that I see here is this one. So my parent has 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a nonane. Substituents are here. This one starts on the 3rd carbon. This one starts on the 2nd carbon. So I'm going to number this way. I have a methyl group. This is ethyl, methyl, and this is that Y, so this is an isopropyl. Ethyl comes first alphabetically, so it would be 7 ethyl, 5 isopropyl, 2, 6 dimethyl, nonane. All right, so draw the bond line representation for 1 tert-butyl, 3 cyclopentyl, 2 ethyl, 4 methyl cyclohexane. So I'm going to start with the parent. That's usually the easiest thing to do here. Then you can build off of that. So 1 tert-butyl. At 1 I have a tert-butyl or turkey claw. At 3 I have a cyclopentyl, which is a 5-membered ring. At 2 is an ethyl. 4 is methyl. Recall that isomers are different structures made from the same atoms. Isomers are not the same, but they have the same formula. A constitutional isomer differs in connectivity. If we look at 2 of the 5 constitutional isomers for hexane, you can see those below. Same formula, different connectivity. There are 3 other ones possible. As you add carbon numbers, the way that you can have constitutional isomers increases dramatically. With C3H8, you have 1 constitutional isomer possible. You go to C9, we now have 35, and it just creeps up and creeps up in that fashion. How can you recognize if 2 molecules are isomers? If you're looking at these 2 structures, are they the same? Do they have the same formula? So there's 2 ways that you can test to see if they're identical using one of the 2 methods. So one of them is to flip the molecules in 3D space and rotate it around its single bonds until it is superimposable on the other molecule. So if you look at these 2 molecules that I've built here, they kind of look different, but if I pick one of these up, I'm just going to rotate my bonds around a little bit, and now they look exactly the same. Those are identical. So one way to look at it is to rotate the bonds in 3D space around each other until they are superimposable on the other molecule. So you can see here, I can rotate it around. Superimposable means I can stack them together and they are identical. So I can put them on top of each other. So those are the same molecule. The other method is to name the compounds. If they have the same name, they are identical. So we can look at this here. This is 3-methylpentane. This is 3-methylpentane. Which method is a surefire way to tell if they're identical? For me, it would be naming, but you could be a person that is a more visual person that can rotate things in their head and make that connection, but I have a hard time with that. Newman projections. We know that single bonds in molecules can rotate, as you just saw. Different rotational states are called conformations, and there's 3 ways to represent ethane. So ethane is CH3, CH3. So there's the wedge and dash method. Remember, wedges mean that it's forward. Dashes mean that it's pointing back. And the flat lines are representing things that are in the plane. There's the sawhorse method, which shows you a front and a back. And then there's the Newman projection, which shows carbons that are eclipsed one in front of the other. So if you look directly down the carbon-carbon single bond axis, as this eyeball is showing you here, this is where it can especially be helpful to have a model, and I'll show you that in a second. The front carbon should eclipse the single bond and the carbon behind it. Here we're looking down this carbon, and we're not going to see this bond in between here, but we'll see the hydrogens on both sides. So show the front carbon as a point. So this is the front carbon, and the circle here is the back carbon. If we're looking at this carbon, I'm just illustrating here what you can see. So this is the ethane. I just have the back carbons in yellow so you get a better idea. You can see the difference there. If I turn this here, this is me looking down the bond, so you can see down the bond as well. This is the front carbon. The back carbon you can't see. This is represented with the point. The back carbon is the circle. So these hydrogens are coming off here at 120 degrees. And these are here. So this is the rotational conformers. You can draw the different Newman projections based off of that. So if we are to draw a Newman projection for the following molecule, our eye is looking down this bond here. So I'm going to draw a dot for that first carbon. And here it is helpful to have a model. So I'm going to have the model built here for you. This is what you're seeing in the picture here. We have the 3 carbons, 1, 2, 3, in the plane, and the chlorine is in the plane. So these are all flat together. And there is the carbon that is dashed, that is pointing back. So that means we have a hydrogen pointing forward. So the bond that we're looking down is this one right here. So we're going to draw what this looks like down the bond. So I'm going to have a carbon here that is eclipsed by this one, or this is eclipsing the one behind it. There's a carbon sticking out and the chlorine sticking out in that direction, and then this one here. So again, we have this point, which is the front carbon. I have an H sticking out up top, an H sticking out to this side, a CH3 sticking out here. And then the back carbon is the circle. This is the chlorine. There's a CH3 and the H here. We have the H sticking up, this hydrogen here sticking to the side, carbon to the side, and a carbon up and to the left, and then the chlorine's up and to the right, and the hydrogen back here is sticking straight down. So we can do the same thing looking at the carbon from the other side. And now we're just switching what is the front carbon. So this is the front carbon now, the one with the chlorine. So we have the carbon that's pointing down, a hydrogen in the back pointing up, and this here. So the front carbon has the chlorine off and to the side, CH3 down here, the H, and then the carbon behind it has an H to the side, H sticking up, and a CH3. So what is the angle between hydrogen atoms on the same carbon? On the same carbon, this is the 109.5. But between the hydrogen on the front carbon and the back carbon, that is 60 degrees. That's also called a dihedral or torsional angle. So if we compare the stability of the eclipsed and staggered conformations, there's repulsion in the eclipse form. So this is the staggered, where everybody gets its own window. When you can individually see all of these hydrogens apart from each other, it's like if you're taking a picture, you want to stick your face in between 2 other people so that you can be seen. This is the staggered conformation and the lowest in energy. And when they're eclipsing each other, or one is behind the other one, this is eclipsed or highest in energy. Not desirable. So in the chlorine structure that we just saw, this would be the eclipsed form, where the front carbon is covering up the back carbon. These hydrogens are covering each other up. This chlorine's covering that one. The staggered form you'd have your groups opposite of each other, and so they're not eclipsing each other, and they can all have their own little personal windows. The difference in energy between the staggered and eclipse conformation is torsional strain. So you can see if you keep rotating the ethane molecule all around each other, it will fluctuate back and forth between the staggered, eclipsed, staggered, eclipsed, staggered, eclipsed, staggered. There's a difference of 12 kilojoules per mole energy there. For butane, when you add 2 carbons, there's a couple of different staggered conformations. This is the anti-staggered, and this one is the full eclipsed. And then this one down here is the anti again. These two are in between here, or in the gauche conformations. And I will demonstrate this for you now. Okay, so in this model I have the butane. So there's 4 carbons. 1, 2, 3, 4. If I look down the second and third carbon, this is my Newman projection here. This is the full staggered, or the anti-staggered conformation, where the 2 large CH3 groups are across from each other. If I turn it a little bit, this is one of the eclipsed versions. So you can see the yellow is behind the orange here. If I rotate it again 60 degrees, this is the full eclipse. So my big CH3 groups are in the way of each other, and if you look here, they're kind of bumping into each other. This is the full eclipsed, and then you go back to here. This is the gauche. So my CH3 groups are not on top of each other. They're just kind of off to the left, but they can still kind of bump into each other if they tried a little bit. And then this is an eclipsed version again, and then we have the anti-staggered. Just the full rotation you go through here. You go between staggered, full eclipsed, another gauche staggered, back to eclipsed, and then the anti-staggered again. So those have the different energy levels there. And notice the full eclipsed has the highest energy, and the anti-staggered ones have the lowest energy. When the methyl groups are farthest apart, like you saw, that is the anti. When the methyl group they're off to the side, this is gauche. And then this one is also a gauche interaction. This one has the least steric hindrance. The least stable conformation results when the methyl groups are eclipsing one another, and that ends up being 11 kilojoules per mole of energy that's caused there. So each CH3 groups that are eclipsing accounts for 11 kilojoules of energy per mole. But you don't need to memorize any of these values here. Just be aware that this is low energy, high energy, in between. Practice drawing. I know you want to practice. Newman projection for the highest and lowest energy conformations of 2,2,3,4,4 pentamethylhexane, looking at the Newman projection down the C3, C4 axis. So first we want to draw hexane. Hexane is 6 carbons. We have 5 methyl groups, 2, 2, 3, 4, 4, and we're looking down the C3, C4. So that's right there. So I'm going to draw the first carbon. On the first carbon, I have a CH3. I have an H. And there's a group over here. So that's coming off of this carbon right here, and then that CH3 and the H that we haven't drawn in here. On the back carbon, I have 2 methyl groups and a CH2, CH3. So this is one of the gauche drawings here. So you can draw on the CH3s if you want, or you can just leave it as is. The anti is going to have the largest groups opposite each other. And here the largest groups are the ethyl and the tert-butyl. So I'm just going to redraw with the tert-butyl on top. So I'm just going to rotate everything a little bit. So I had tert-butyl, CH3, and then H, tert-butyl, CH3, H. And on the back carbon, I'll just leave the ethyl where it is. This is the anti-staggered, that's lowest in energy. To draw the highest in energy, we're just going to put the largest groups that are on the carbons eclipsing each other. So here I'm just going to leave the tert-butyl group where it is, CH3H. And on the back carbon, we'd have this CH2, CH3, CH3, CH3. So this is the eclipsed. This is highest in energy.